Let me now show you a very simple way of visualizing quantum states of a single qubit and operations that we perform on a single qubit. If you take any state of a single qubit, state psi, you can conveniently parameterize it using two real parameters in this case. Well, we just neglect the global phase factor. So it's going to be cos theta over to 0 plus ei phi sine theta over to 1. Now, when I write it in this particular form, I can then think about another vector called the Bloch vector that I somehow mentally associate with this state vector, and that Bloch vector that you can see here on this diagram in terms of the spherical coordinates will be a unit vector that is characterized by or defined by the two angles, the polar angle theta here and the azimuthal angle phi here. So I have this one-to-one correspondence. Instead of thinking about the qubit being in this particular state, I can think about a unit vector in three-dimensional Euclidean space pointing in some direction that is specified by theta and phi. Now, when it comes to unitary operation on a qubit, let me first mention that any matrix, doesn't matter whether it's unitary, Hermitian, whatever, any matrix whatsoever, that is any 2x2 matrix in this case, can be conveniently decomposed in the Pauli basis. So I can write any matrix of this type as sum over k, m sub k, sigma sub k, by which I mean m0 times sigma 0, which is really the identity, plus mx sigma x plus my sigma y plus mz sigma z, where mx, my, mz are in general any complex coefficients, and the same stands for m0 here. The physicists like to write this part as a kind of a scalar product of a vector m with components mx, my, mz, and sigma, where the vector sigma is sort of having matrix components sigma 0, sigma x, sigma y, and sigma z. Now, of course, unitary operation is not just any operation. We have to add this, we define it by the condition that u times u dagger is equal to the identity. And if you take this into account, then you can write any unitary matrix using this kind of basis in the following way. So any 2x2 unitary matrix can be written up to a global phase factor, can be written as cos alpha over 2 identity plus I some unit vector n dot sigma, so this is this kind of scalar product sine alpha over 2. So you can see that any unitary matrix up to a global phase factor acting on a qubit can be characterized essentially by three parameters. So that is alpha, and the other two real parameters specify the unit vector n. Now, this unitary operator, this unitary matrix has its meaning when it acts on a Bloch vector. So let me just, one thing that is convenient giving lectures within this kind of setup, that I can actually draw all those more complicated diagrams before I start recording. It took me actually a while to draw a sphere. Every single time I tried, it became kind of a potato. But anyway, so this is my Bloch sphere. Okay, so then you have the Bloch vector, but now I'm going to put another vector on the Bloch sphere that is going to correspond to unitary operator u. So that's this vector n that I have here, a unit vector n pointing in some direction. Now, alpha then has meaning of angle of rotation. So what this unitary operator does, it rotates the whole Bloch sphere, and it rotates it by angle alpha about the axis that is specified by the unit vector n. So in particular, if you act with this unitary operator on the state vector psi, then one way to think about the result of this evolution is to think about Bloch vector being rotated by angle alpha about the axis that is specified by the unit vector n. And in fact, this rotation is either clockwise or anti-clockwise. Well, actually, anti-clockwise is corresponds to the minus sign here, and that's the usual convention. So we have a very nice illustration of single qubit operations. You can think about sequence of unitaries acting on a qubit as sequence of rotations in three-dimensional space that take a state vector from its initial state, and by a sequence of rotations you generate some other Bloch vector that then you can just map back to a given state vector. So in particular, you can, for example, if you look at the Hadamard can be written as a sum over 1 over square root of 2 sigma x plus sigma z. So what it really corresponds in terms of rotations, you can figure out that the n vector here, the unit vector, is given by those three components. So it has only x and z component. And it corresponds, the angle alpha corresponds to the rotation by 180 degrees. The Hadamard in this language of rotation corresponds to the rotation about the axis that is the diagonal in between placed in between x and z, and then you rotate by 180 degrees. So essentially you can see that you flip x and z axis by performing the Hadamard transformation on the Bloch vector. This will allow you to visualize certain things. So I'm not saying that this is a sort of a beautiful universal tool. It works for qubits, but unfortunately we cannot extend this construction to higher dimensions. But it's good enough. Lots of operations will be restricted to qubits. So you will see that thinking in terms of rotations will actually help you to understand in a very intuitive way what is actually happening to a qubit. Well, to those of you who are more mathematically minded, essentially what I was talking here about was about isomorphisms that you have between the quotient group U2, U1, and the group of rotations in three-dimensional space. As it happens, the composition of unitary operations on single qubit can be nicely visualized as a composition of rotations in three-dimensional space.